Hi guys, happy Friday. I want to start today by explaining why we're talking about pressure. So, pressure is, well, we've been talking about gases, and gases are, we know, small, hard spheres with zero volume. Their motion is rapid and constant and random, and their collisions are elastic. And so, what you can really quickly see about gases is that they are moving all over the place all the time. And so, because of that, they're constantly colliding with each other. But more importantly, they collide with the container walls. You may not feel it right now, but there are gas particles just bombarding you right now. They're colliding with you. And that's what keeps you in, right? You have gas on the inside of you. That's what keeps you from not like expanding and then exploding. And if you've ever taken a bag of chips up in the mountains, what you can see is that that regular bag of chips, it expands as you go up. And that's because the pressure, the gas that was on the inside, is providing a pressure to the outside of the bag, but the atmospheric pressure is getting lighter. And that's kind of what we're explaining today is we're understanding how pressure works. So pressure starts or gas starts with a lot of collisions, and that brings pressure. So we're going to define and explain. We're going to look at the math that goes with pressure. I'm going to take my first try at teaching you guys math using this program. So if you've ever been to a science museum, I know, nerdy, it's okay that I like science museums, then you have probably seen a bed of nails. I know that the California Science Center, the Science Cube that's in Anaheim, they definitely have a bed of nails. And I've definitely laid on it because I thought it was cool. You see them in Aladdin or other shows, and it's pretty amazing to think about being able to lay on a bed of nails. And the idea is that we're talking about a force per unit area. So the person on the bed of nails is exhibiting a force, a downward force on that particular nail. So I usually draw on the board for this, so I'm gonna see if I can work it out. Okay, so I think I'm gonna, oops, nope, this one, sorry. Okay, so if you were, oh well, I just knocked myself over. If you were laying on a bed of nails, oh, you know what? I don't know if this, well, we'll see. If you were laying on a bed of nails and you were a person, this is me drawing a person, you can see that I'm no better at drawing now than I ever was when we were in class. And this person was laying on just 4 nails. That would really hurt, right? That would be a lot of pressure on that person's body. But if we increase the number of nails, then we start to make this person's body feel a little bit more comfortable. And so we describe this situation, this phenomena, as pressure equals force per area. Now remember, just like in class, I don't mind whether or not you write things down that are on the slides, but you should definitely write things down that I'm writing on the board. I'm putting it up here because it's hard to explain. So you should have a note to yourself. Okay, you should be writing this down, taking notes on it. Let's see if I can try to not knock this whole thing over. Stay. Okay. Is force per unit area. It looks like it was going to fall. Okay. So we are talking about pressure, and what we see with pressure is that we have force per unit area on a surface. And this is the result of collisions by gas particles against any surface. So if you look up here, this is supposed to be illustrating a bunch of gas particles, and they are zooming around, right? Constant, random, rapid motion, zooming around, and they're colliding with the container walls. And every time they hit the container wall, they provide a little bit of force. Like imagine you had like a bouncy ball or something, you're throwing it against the wall, you're going to eventually create like dents in the wall, right? You're creating this force against the wall. We say that pressure is force per unit area. And so any gas that is contained exerts a pressure inside of the walls. And so again, back to our bag of chips, right? And going up the mountain, the gas that is contained inside of that bag of chips is colliding with the surface of the bag and pushing, inflating the bag out. So that's what is creating that pressure. In order to decrease pressure, you can either increase area or lower the force. And that kind of brings us back to this visual of our bed of nails. And so what we're saying is, I have two choices if I want to decrease the amount of pressure. Okay, so the pressure is happening right here on each nail head. That's where the pressure is happening. And so what we need to think about is what amount of weight is pushing down on the nail head, okay? The unit area of the nail head is really, really small, but if we can put more nails, then we're putting less weight down on the nail heads, and then they're not really so painful. If you ever have tried this at a Science Center, you'll know that it really doesn't hurt. What would hurt, though, I always think about is how do you get on to the bed of nails? I mean, in the Science Center, they put like this plexiglass up, and then you lay on the plexiglass and they lower the plexiglass down. You can kind of see there's like a spot for his head. And then this plexiglass would like come back up. And so he'd be able to get on and off the bed of nails without getting hurt. But I always wonder, that would have been like the tough thing to do. Like you don't want to run and jump on a bed of nails, would you? I wouldn't. Okay. On Earth, we have gravity, and gravity is a force, and we're really not going to get involved with it. That's a physics force, but you can believe me or you can Google it. Gravity, as we spin around, forces gases to stay around the Earth. It has to do with how fast we're spinning, which has to do with the length of our days. And as you talk about other planets and you think, oh, well, how's the length of their day? Well, if they're spinning slower, then they don't have as much gravity pulling down. So gravity is going to keep the gases against the Earth. And we call that specific amount of gas that is trapped between the crust and space, okay, that is trapped by gravity. We call that the atmosphere. So collectively, the atmosphere exerts a pressure on the Earth's surface and also on you. So you are being bombarded by millions of tiny gas molecules that are running into you constantly and creating this pressure on you. This pressure is mostly made of nitrogen and oxygen. The world that we live in, the atmosphere that we live in, is mostly made of nitrogen and oxygen. So atmospheric pressure is equal to 101,300 pascals. Pascal, like Pascal's triangle, he was a Renaissance man. He did lots of things, not just geometry, but Pascal was the one who came up with the measurement. 101,300 pascals is an annoying number. And so we simplify that number 3 different ways. So you actually don't need to know the 101,300 pascals, but what you do need to know is a kilopascal. So remember, kilo is 1,000. So we move our decimal place 3 places to the left. So it moves, yeah, and we get 101.3 kPa. So that's one standard measurement of the amount of pressure that is on us from the atmosphere of gas that is trapped by gravity. Another measurement of it, my personal favorite, is an atmosphere. We have 1 atmosphere of gas on us because we are on Earth, and so the amount of gas that is running into us is equal to the amount of gas that is trapped on Earth, and so we are under 1 atmosphere of pressure. There is a third unit you need to know, 4th unit altogether, a third unit that you need to know that is measured in millimeters of mercury. And to understand millimeters of mercury, we need to look at a barometer, and Torricelli, who is going to tell us about a barometer. So this is Evangelista Torricelli over here, and he came up with this idea of how to measure atmospheric pressure. So what he does is he takes a tube, okay, right here, this thing he's holding is a tube that is full of mercury. If you've ever played with mercury, don't, it's dangerous. It gives you mercury poisoning and it kills you. But if you ever did see it and you ever did play with it, mercury is a really cool solidy liquid. It's kind of like a stress ball, you know, where it like is kind of a liquid and it's kind of a solid, a non-Newtonian liquid, which is a nerdy way to say what they put inside of a stress ball. So mercury is like a very thick fluid. And so what he did is he filled a container of mercury, a thin tube of mercury, and then he turns it upside down in a bath of mercury. This is similar to like if you had water in a bathtub and you like had a cup full of water and you flipped it upside down in the water would stay inside. The mercury stays inside of this tube and it stays, so this is like an outside barometer that you can use. So there's mercury down here in the bottom and then there's mercury in this tube. And what happens is that the Earth's pressure, I have to draw it. I can't, okay? So the container, let me erase this. Inside of the container, or like on a plate, okay, we have a plate and there's mercury in here. And then there's this long tube, okay, that also has mercury in it. And it has just a tiny bit, just a teeny tiny bit of mercury in it. And the mercury wants to come down the tube and roll out into the liquid. But the atmosphere is all around it. And so we have our oxygen gas and our nitrogen gas, and they are pushing against the mercury. And they're pushing the mercury back up into the tube. And so we hit this balance, okay, this balance of the pressure from the atmosphere pushing the mercury up and the gravity pulling the mercury down. And that happens at 760 millimeters high. It's a measurement, like a height measurement. So we say 760 millimeters of mercury is when the atmosphere balances gravity on mercury. And so that is another pressure measurement that we use. This pressure measurement, these pressure measurements can be converted between. So that's what we're going to be doing for the very end of today, is we're going to do some conversions. So what we know now is a set of standard pressures. So we have 3 standard pressures. We have 760 millimeters of mercury. These are going to be a little different than what you're seeing on the screen, so I really encourage you to write them down. I'll go to this. We have 760 millimeters of mercury. We have 101.3 kPa or kilopascals, and we have 1 atmosphere. And all of these things are equal to each other. So when we do a conversion, if I were to ask you, say, we have a pressure of 450 kilopascals. And then I said, what is that equal in millimeters of mercury? I would, and I'm reading right now off of sample problem 13.1 on page 387 in your book. If you wanted to, you might pause this right now and go to that page. So I have 450 kPa, and I want to turn that in. I want to find out how many millimeters of mercury is that. Okay, so I'm going to do a conversion. Yay, conversion factors. Okay, so I start with 450 kPa as a fraction over 1. Now, kPa, just like always, is going to move down to the bottom of this fraction. And what I want is going to go on top. Here's the great news. Pressure conversions are only ever 1 step. Okay, there's no 4 steps or anything crazy. So what I'm going to do now is I'm going to put in my standard pressure values that are here. These are standard pressure. So I'm going to put in my standard pressure values. So what goes with millimeters of mercury? 760. What goes with kilopascals? 101.3. So what we would do now is we would solve this problem. We would do 450 kilopascals times 760 divided by 101.3, and we would get an answer. The answer to this particular problem, let's see, in millimeters of mercury, is 3,400 millimeters of mercury. 3400 mmHg. Okay, there is my answer for that one. And it may be rounded a little differently than you guys are used to because I'm using the book's values for that. And the book sometimes does some like tricky rounding stuff. So that is how you do a conversion. And so these are our 3 different values for pressure, and we can convert between any one of them. Not tomorrow, but Monday on our Zoom, after you guys take your quiz, I will go over a few more of these, but I'm going to have you guys practice some for homework. Okay, so you're going to be turning in homework on Monday. I know that our due dates have kind of changed a little, but you're going to be turning in homework on Monday that shows me that you guys have attempted this. So you're going to do practice problems 1 and 2 on page 387, as well as section assessment numbers 3 through 6. So I'm going to be, I'll be posting that on Google Classroom, but just so you have an idea. And so we will talk more about that later. All right. Thank you guys for watching. Talk to you later. Bye.